Okay, very nice. So here, uh, quick view. Let me go back to my original view. Okay, very nice. This is the geometric memoryless property that we discussed so far. So just to sort of be pedantic, just make sure that just to understand this quotation remark in the following, this takes the range of this random variable. The range is n plus n, n plus 1, n plus 2, and so on and so forth. And you should understand the fact that x equal to m plus k, given x is equal to m, x is at least m, this probability was the same as the chance that x is equal to k. That's what we showed. Okay, very good. And that's how I understood this quotation remark. Oh, very nice. So now we do one more important example, and then I'll sort of move on. So the example is kind of important. We have this. You may have seen this also in class 12 or otherwise as well. Is the idea of multinomial distribution. So let me just quickly do this. So here the so this is a very specific example that I'd like to sort of do. Let me just so this is example 3.2.12 in our book. So the examples are following. So before we did only the binomial case, there were two outcomes. So now let's assume there are k outcomes. Suppose an experiment has k outcomes. So so each time you do an experiment, there are k possible outcomes. So one or like so success and failure, you have many outcomes. And let's say each outcome has each outcome j, each outcome j has a probability pj of a probability pj. Okay. So probability pj of occurring. So each outcome has a probability pj. So now I want to understand, let's say, how does this experiment behave? So now this is again a place where random variables become very useful. So if I were to write out this whole thing in let's say we perform n trials. We perform n trials of the above experiment. N independent trials. So now if I do this now, if I would write out all the events and all the outcomes in a sort of I have n trials, each trial has j outcomes possible. I write out all the sample space completely and I try to use that to compute the events and the probabilities of the events, it'll be quite hard to do. So what we do is, this is where random variables again come into use. So you let xj, do the, very careful, x sub j is the number of trials among the n in which the jth outcome occurs. Okay, so number of trials, number of the n trials that result in the jth outcome. Okay, is that clear? So that means I'm just doing this random variable. So one thing is clear is that so they're clearly dependent because of the following idea. If I look at x1 is the number of trials in which the outcome 1 appears. I look at x2, the number of trials in which the outcome 2 appears, and I go all the way till k, and I get x sub k, right? if I add all these up, I'll always get n. Right? So this is observation. So observe. So they're clearly dependent. So they're not independent. Of course, so therefore not independent. So the x's are not independent because the sum adds up to n. So there's a clear relationship. So if I know x1 through xk minus 1, then xk is uniquely determined. This is one important fact. Very nice. So now, how do I do this? How do I find? So this is the first interesting example where we need to find. Let's say I want to find the joint distribution of x1 to xn. So the joint distribution of x1 through xn. And that's the first question I have. How do I do this? So now this is called the multinomial distribution. We'll discuss that as we go. So how does one do this? So now, what do you want to do? You want to find the chance that x1 is equal to x1, xk is equal to xk, sorry, and xk is equal to xk, right? And what happens to the xk's? Each of the xk's can be take values from 0, 1 up to n, and you have one condition that the sum from I equal to 1 to k of the little xi's add up to n. Because there are n trials, so maybe I should use j because I've been using j, so I'll use j here, so I'll use j here, so I'll erase this. So I have x sub j, and the j outcomes can come from 0 to 1 to k. So I have n, let me just do one, yeah, that's right. So how does one do this? So what does one do? So here one should be a little bit careful and one should see how does one exactly compute this probability. So let you think a little bit on this and let's see how do you want to do this. How do you compute? If I give you a sequence of x1 through xk, how would you do it? So here the idea is the following. It's very easy. So now let's look at the event. Let's look at the event b of x1 xk. That means the outcome 1 appeared x1 times, outcome 2 appeared x2 times. So let's define that as the event x equal to x1, x equal to xk. Right. Let's define this. So then you know that the chance that of the event b of x1 through xk, right, is the same as the sum over all omegas, that is all the sample points in the event bx1 through xk times the and at each sum you add the probability of omega. Right? This is what you do. Right? This is how you would compute the probability of b. But look at any element. Look at any element in b of x1 through xk. Right? So this is a sequence of n trials, and look at each outcome. You want outcome 1 to appear x1 times, outcome k to appear xk times. So then, so this is observation. So this is observe in omega. The sequence is an n tuple where outcome j appears xj times. And that's how omega looks like, right? in omega. So now, if you want to compute the probability of omega, they're all independent trials, and you know outcome J appears xj times, and you know outcome J comes with probability P sub j. So this is just going to be the product of j equal to 1 to k. Outcome J occurs with probability Pj, and it occurs xj times. That's how it will be. So therefore, right, this because this happens, and Pj is the probability of outcome J. So once you have this, then if you want to compute the probability of B, so the same that this will immediately imply, let me go back to black, the probability of B of x1 to xk is the same as the sum over all omegas in the event P of x1 to xk, and each of them has the same probability. So the same probability is this probability. Let me just copy this. Let me duplicate it. Put this down here for you. So same probability, right? But now they're all the same probability because it doesn't depend on what sequence it was. Right? So this is just going to be the same as the size of B of x1 through xk times this probability. Right? That's what's good. How do you find the size now? So size, how do you find? So size, what do you have to find? You look at the number of outcomes such that you have k boxes, you have n, you have n boxes, so you have n balls and k boxes, and you have to put the j outcomes in. Okay. So this is the same as this computation. Let me write this down in a bit more precise manner. So this is the same. So now you observe that b of x1 through xk, the size of this is the same as saying you have n balls, you have k boxes, and then you have to do that xj falls in xj of them fall in box k, box T. And you want to know the number of ways. Right? So number of ways of allocating n balls in k boxes such that xj falls in, xj of them fall in box T. So let me just cut and paste this a little bit. It's too close to this whole thing. Let me just bring it down. So what I want. This is what I want. So once I do this we know from either high school or whatever is the same as you look at n factorial at the top and you have x1 factorial all the way to xj. So therefore, the joint distribution of x1 equal to x1, xk equal to xk, right? This joint distribution is the same as you put the size of b as n factorial by x1 factorial, xj factorial, and then the product from j equal to 1 to k of p powered p sub j to the power x sub j. So that's the joint distribution. Of course, I assume several things. I assume that so this will come out. So therefore, this will happen only in the two specific conditions have to be satisfied. Let me just move this down this side. Therefore, this happens. Let me erase the k. This k. So when does this happen? So let me erase this part as well. So when does this? Let me move this down a little bit. So very good. So let me erase this part of the notes. So this is equal to this. Under what conditions now? This happens with if each of the xa's are between 0 and n, and we use the fact that the sum of j equal to 1 to n of the xj's, j equal to 1 to k of the xj's, sorry, 1 to k of the xj's was equal to n. Right? Under this condition, this happened. Otherwise, the probability is 0. this is the kind of the joint distribution of x1 to x3. So let me just do split screen so you can see everything in one shot. Let's try and see if I can get that now. Here, add it again. Very nice. Very nice. So I go down a little bit before, and I have to go to the previous page here, and here I have to go to the last page. Very nice. Very good. So this gives you a complete view of the multinomial distribution. That is, I start off with the experiment. They have k outcomes. I perform n independent trials. I'm interested in how each outcome, the type of each outcome in each trial. So the way I do is I just count the number of times an outcome j appears, right? And then I compute the joint distribution of x1 through x2. So even though the trials are independent, if we were to count the outcomes of each type, they become a very dependent sequence of random variables, and this gives rise to what's called the multinomial distribution. And it's a very powerful tool. And you can also check the following fact that if at n equal to 2, you will get you can go back and get the binomial. So in n equal to 2, you'll count how many times 1 appears and how many times 0 appears. But if in n equal to 2, if you know 1, you know the other guy immediately. So there's no really calculation. Give me 1 second. Just, get this out. Very good. So now I want to sort of move on to, so just one small observation before I sort of move on is that just check n equal, k equal to 2, not n equal to 2. I said n equal to mistake. So let's say k equal to 2, then just see connections to binomials. Something you should just check and see if you can observe. I'm observing both x1, x2 here. So in binomial case, if x1 plus x2 is n, if x1 is, I'm only counting the number of successes, means I'm just looking at x1, not x2. Okay. So binomial p1 or binomial 1 minus p. So these should just put here n. And n. Minutes. Let me go back to my full screen view. Oh no, not split screen. No split view. Minutes. Very good. Very good. So now I'll close today's class with another idea that is kind of useful. It's like functional random variables. So here's the section is 3.3. So I'll do only examples. I won't do I'll come define it next time. So 3.3 is functions of random variables. So let's do a bunch of examples. And let's come to the formal definition after I do the examples. So let's do a simple example first. Let's say X example. Let's do example 3.3.1. So let's say X is a random variable that takes values uniform random variable that takes values, let's say in -2. So it takes uniform value, choose a number uniformly between -2 and 2. So 0, 1, and 2. That's what x does. And let me now take a function. This function is from the real line to the real line, and given by, let's say, f of x is equal to x squared. Okay. So now I just call my random variable y as f at x, and I ask you the question: what is the distribution of y? So now the idea is that, so first what I do, I find the range of y. So what is the range of y? The range of y is x is -2, -1, 0, 1, and 2. So range of f of x, f at x, that is just the set. What will it take? It will just take the values. When you square 0, you get 0. When you square -2 or 2, you get 4. When you square 1 or -1, you get 1. So this is the range of x. Then our next thing I will do is to find the distribution of y. I have to find the chance that y is equal to y for every y in the range of y. So y is equal to y is what? For y in the range of y. So how do I do that? So y has 3 values. So chance that y is equal to 0. So that happens when only in one case. That is, when y is 0 means x squared is 0, and that's the same as saying x is 0. Right? Then nothing else happens. So that's the same as, so there are 6 possible outcomes in the uniform. So that's just 1 over 6. That's it. So distribution of x, we know that the chance of x equal to k is equal to 1/6 for k in -2, -1, 0. So I'll rewrite this in green so it's clear. That is an observation. So that is uniform means the chance that x is equal to k is 1/6 for k in -2, -1, 0, 1. So this example, if you do y equal to 0, that means x has to be 0. It can't be anything else. So that means x 1/6. So let's do x equal to 1. So chance that x is equal to 1, so let's erase a little bit. Y is equal to 1, sorry. The chance that y is equal to 1, we do y equal to 1, what do I get? That's the same as x is equal to 1 or x is equal to -1, right? Because if x is 1, also y is 1. If x is -1, that also implies y is 1. So that's the same as the chance that x is equal to 1 plus the chance that x is equal to -1. And if you add the two up, I get 1/6 plus 1/6, I get 2/5. Oh, sorry. So is it 1/6 or 1/5? I'm sorry. How many numbers are there? There are 1, 2, 3, 4, 5. I'm sorry about that. Yeah. So there are 5 numbers, so I should just correct this a little bit. This is 5, this is 1/5. And I come down here, and this is all 1/5. Sorry, this is 1/5. So this is, I go back again, I go 1/5, and this is 1/5 plus 1/5, and that's 2/5. Very nice. And then similarly, the chance that y is equal to 4, that's the same as the chance that x is equal to 2, or x is equal to -2, and that if you compute the computations, you just get again 2/5. So that's the distribution of y. So y takes along with this is called star, let's say called star, and this, let's say it's called star prime. So star and star prime give you distribution of y. Right? So star and star prime. So the range of x, range of y, and the distribution of y, and the probability how it distributes the weights on the range gives you the distribution of y. y, I'll write y as f of x. So this is one procedure by which you can compute. Let me make this a little smaller so you can see the whole screen in one shot. A little bit more smaller, maybe. Very nice. So this is in one shot. You can see how to compute the distribution of f of x given the distribution of x. So here the function was not one-to-one, but so you have to be a little careful. You have to go and sort of find the exact values of x for which match to the values of y and compute the probabilities. Excuse me. So let's do a simpler, another simple thing we have seen before. So here's another example. Let's say I take two random variables this time. So let's say example, let's say 3.3.3. So let's say I do the following. Let's say I toss a coin once. I look at the number of successes. I toss a coin again, number of successes. So let's say I look at x is equal to x is Bernoulli p. It's a biased coin. Okay? And then y is also Bernoulli p. So let's assume 0 is less than p is less than 1. And let's also assume x and y are independent. I do these two things. And then I tell you, I give you a function of x and y. I give you z is a function of x and y. And I say f is a function from, I'm writing it a little bit complicated just sort of to make sure that I capture the generality of it. Of course, the idea is very simple. So I look at f of x comma y as x plus 1. So look at this, and I ask you to find the distribution of z. So now you stare a little bit like this. So what's going on? You're just nothing much is going on here, right? Because all you want to do is you want to find z is equal to f of xy, which is just x plus 1, right? Now observe this. This is observe. So this is just looking at x and y are two independent variables. So if you go back to the experiment idea, you already know the following, that x is independent of y. That means I'm observing the number of successes in two tosses, and that's the same as a Bernoulli binomial 2, 2, right? Because what we observed is that this person right here is the number of heads or number of successes in two trials, and that's one way of understanding. But in general, if you want to sort of, if you don't want to go to experiments and you want to do it directly, you have to be a little bit more careful. So how does one do that? Let's just check that a second. So if you want to do it in a sort of methodical way, you have to be a little bit more careful how to do it. So let's see. How does one do that? One needs to be a bit more careful. So one has to write out the events properly. Let's do this for the example, then it'll be clear how to do it in general. So here you can do it, you can compare to experiments and do it. But the correct way to do it is that first you observe, like if you like to do the previous example, you observe that the range of z is going to be what? So x and y are Bernoulli, so x takes value 0 and 1. So this is going to be 0, 1, and 2, right? So this is because range of x is 0 or 1, and range of y is also 0 or 1. So then what you have to do is, if you want to compute the probability of z equal to 0, When will this happen? This will happen when x and y are 0. That's the same as saying the chance that x is equal to 0 and y is equal to 0. And this will be the same as use independence. Use independence here, independence. And you'd get the chance that x is equal to 0 times y is equal to 0. And that's the same as p squared, or 1 minus p squared. 1 minus p, and that's the same as 1 minus p squared. Similarly, if you do probability that z is equal to 1, you can write out all the combinations. Right? You can say that the same as happens in x is 0, y is 1, or x is 1, y is 0. You split that up into two sums, x equal to 0, y equal to 1, plus the chance that x equal to 1 and y equal to 0. And then you use independence now to say that x equal to 0 times the chance that y is equal to 1, plus the chance that x equal to 1 and y. So here I've used independence. And then I would get the fact that this would be just same as p times, say 1 minus p times p. And this would be the same as 1 minus p times p. And I would just get the correct answer. So I would get 2p times 1 minus p, which is what I want. And you can finally conclude that z equal to 2 will have all possible combinations, like x equal to 1, y equal to 1. That's the only possibility, and that's just by independence, x equal to 1 times y equal to 1, and that's the same as p squared. Okay, so I'll build on this next time. I'll take a 2-minute break, and I'll come back.